Okay. Sorry, I'm a minute late. So last time we got into the heart of the support vector classifier. So let's just quickly review because there's a lot of different things we talked about. So we start with this picture. It shows the geometry of the linear classifier. And one of the big things we got from this picture is that the sign distance from any point to the boundary can be written this way in terms of the classifier parameters. Then we talked about linear separability. We know intuitively that just means you can pass the boundary between the two sets of labels, training points for one label and the other label. But then we wrote it a little bit more precisely. And the final form we got down to was this one. We said, if the data set is linearly separable, that means there exists some classifier parameters so that you can write this for all your training features. So this is Z, the linear score for the ith training feature. That could be positive or negative. This changes the sign on it so that it's all positive, and in fact, it's all greater than 1. Okay? And then we furthermore said, well, actually, we can combine that with this equation to write this Zi term as gamma I W, and we finally got this here, which says if we have linearly separable data, then there exists some parameters W so that this acts as a lower bound on this sign corrected distance. So this is the distance here, which is going to be positive for half the samples and negative for the other half. This corrects the sign on the distances so that these are all positive distances. And this now says they're lower bounded by this amount. We said that that can be useful if you want to design a robust classifier that maximizes the minimum distance to all the samples. A non-robust classifier that is still linearly separable might look like this, but you can see it's getting very close to the training samples here. So if we instead, on one hand, make sure we have linear separability, on the other hand, we maximize this, we can put the boundary exactly, can orient it exactly like this, where it is maximally far from all of the training samples, or from the closest training samples. This quantity here is called the margin. That's the lower bound on the minimum distance. So that's the main idea, basically. And that leads us to the method. So if we want to maximize this, 1 over norm of W, then we should minimize the norm of W, or equivalently minimize half of the norm of W squared, such that we maintain linear separability. And if we solve this optimization problem, which ends up being a convex problem, we get exactly this boundary that we want. So that's the main idea behind this maximum margin classification. When we do this, it turns out, you can kind of see this from this picture, that the boundary is going to be completely determined by the closest training samples here. The locations of all these other ones are not involved at all in coming up with the boundary. So these few training samples are what we're now focusing on. Those are called the support vectors. So those are the main ideas behind this maximum margin classification. So this is a good time to pause. Are there any questions on this? Okay. Okay, so the trouble with this is that in order to use this method, you actually have to have linearly separable data. So if one of the black points is over here, you simply can't use that method. It just doesn't work. And so what we did next is we extended this method to make it deal with data that is not linearly separable. And so to do that, we started with this constraint, which we said this is how we write linear separability, how we wrote it at first. Then we just move this term to the right side. And this is what we would need to do for all samples I for the hard margin classifier. But now we're saying replace that constraint with this cost. And this is a cost so that if, in fact, you can satisfy this constraint for all I, this cost will be 0 because these terms will always be 0 or smaller. And so the max will choose 0 and the total cost will be 0. But if that's impossible to do, the cost, you can still handle that sort of data, but the cost will just be greater than 0. So we basically plug this into the method. So instead of doing this constraint thing, we instead introduced this. We add this to the previous cost. We get this new cost. And that brings up one other important consideration, which is how to balance the two cost terms. So we said, let's put in this tunable parameter called C. C should be positive, but we can choose it. And as C gets larger, that means we care more about this cost than we do this regularization term, which means that we will allow this to get larger so that we can make this smaller. When this becomes larger, the width of the street shrinks. So the street being this thing. On the other hand, when this grows smaller, that means we want, we allow this to be bigger, but we will try to make this smaller. Okay, so these are the pictures we saw. So when you have large C, you tend to get a narrow street, which means there's only a few support vectors determining your boundary. On the other hand, when you use a small c, you get a very wide street, which means there's many support vectors. And probably the most useful way to think about this is as a bias variance trade-off. So when you have only a few samples determining the boundary tends to be very good in terms of not making errors. On the other hand, when you have many samples determining your boundary, you can get situations like we have in this picture where you see that there's more classification errors made on your training set. So we would say that this has high bias, low bias. On the other hand, this has high variance because if you imagine repeating this experiment over and over again for different random training sets, you would notice that this line would be moving around, the boundary would be moving around. But if you did the same over here, because this boundary is sort of like an average of all those points, it wouldn't be moving as much. So this has high variance, this has low variance. So as you change C from high to low, you just navigate different points in the bias variance trade-off. And that's great because we know how to handle that. We just do cross-validation. We hypothesize a grid of different C values. We try them all, and we choose the one that minimizes our cross-validation classification error rate, or whatever we're interested in minimizing. Okay, so those are the main points in this method. This is called the support vector classifier. Are there any questions on this one? Okay, so we can use this with any data set. Does not have to be linearly separable. Then, in order to understand what's happening, we compared our SVC to logistic regression with this ridge penalty, and we saw that they look very similar. And then we plotted the terms that differ between these two methods, and we saw that once again they do similar things, but the main difference is that with logistic regression we get this loss term here that smoothly transitions, whereas with SVC we have a hinge loss, and the hinge loss is exactly 0 above this threshold of 1, and increases linearly below that. So when we look at logistic regression, it uses all the training samples to make its design. This red line never actually goes to zero. So all the training samples are used to come up with W and B. But with the SVC, we're only going to involve those training samples which give us a positive loss. And so that excludes any training samples for which Z is greater than 1. Okay, so that's another way to understand how there's a finite number, a finite subset of support vectors in your training data set. Okay. We also briefly looked at a different way of writing the SVC that you might see in other sources, where you define these slack variables, which are just the things we have inside here. And so then you write that first sum in terms of the slack variables, but now in order to capture the structure of the slack variables, you add a couple of constraints. So now we're back to a constrained optimization problem. It does the same thing, it's just written in a different way. In some sense, these slack variables are pretty interpretable. They're just, they measure whether you're on the good side of the boundary, in which case the slack variable is 0. On the other hand, when you cross into the street, or you even go further and you go onto the wrong side of the street, the slack variable just gets larger and larger. Okay, and we briefly talked about a multi-class SVC, where you can jointly train all the weights and all the B and W terms. Simpler, computationally simpler option is to train each pair of B and W separately. This is in the one versus rest methodology. You do B1 and W1 are class 1 versus not class 2, not class 1. The next are class 2 versus not class 2, and so on. So you could treat each as a binary problem, design the binary SVC, or you could do this more expensive approach. And this latter approach tends to work a little bit better in my experience, but it's more expensive. So here's a final implementation in scikit-learn. We use svm.linear SVC. We have to tell it what kind of loss to use. By default, it uses the squared hinge, not the original hinge that we've been talking about. That makes the optimization faster, but the performance a little bit worse. So let's use hinge. And again, we have to say which of these two strategies we're using here. So to try to get the best performance out of it, we'll use Kromer-Singer. And in doing this, we get 90.7% accuracy on our MNIST data set, which is outperforming logistic regression by 0.5%. So that's great. We improved on what we were doing in the last unit. However, after all this work, it's maybe a little bit of a letdown that all of this led to just this small performance increase. So the good news is that we're not done yet. We have still the big improvement to make, and that's what we'll be talking about today. Before we move on, are there any questions? Anything from last time? Okay, great. So, all right, so the main idea is, as we've seen, support vector classifier works very well when the features are nearly linearly separable. So obviously, if the features are perfectly separable, then it seems like this is a great thing to do, because we get a perfectly, we have this maximally robust classifier and all that, but in practice, we don't have that. However, we did see MNIST not linearly separable, but it was maybe good enough to get this to do a little bit better. So the question is there some way to pre-process our features to make them more linearly separable? And the answer is yes. So it's just one picture. It kind of goes like this. Imagine that I have these raw features, two-dimensional space like this. And in this case, as you can see, there's no linear classifier that can perfectly separate them. However, I could make a nonlinear classifier that does the job. However, if I can somehow do some transformation of these two features into, in this case, three features. So we're going to a higher dimensional feature space. Maybe if I build that well, I can enhance the linear separability of the data set. So here you can see it is possible now after this transformation to pass a plane cleanly between the red and blue classes. So now we might expect that in this case, the support vector classifier that we designed, which was linear, will actually do much better than in this case. So that's sort of the idea. Is there a way to transform our features to enhance linear separability? Okay, so one option to do this is to have some particular explicit transformation in mind, like here, or I'll show you another picture on the next page. But in practice, doing it that way is expensive for reasons we'll discuss. And so there's actually, as we'll see, there's a way around that called the kernel trick. And the kernel trick allows us, as we'll see, to in fact use even infinite dimensional transformations, at least in certain cases. And by doing things that way, number one, you'll see we get really great performance, low computational complexity, and we never need to do any explicit feature transformations like this. We just will need to use something called a kernel. Okay, so let me explain that in due course, but basically that's the last stage of this evolution. So until now, we've defined this support vector classifier. So now, as a way to make this a really good technique, we start with that, and there's two ingredients: a feature transformation and the kernel trick. Okay, so without further pause, let me show you another example, a little bit more concrete. So if I have this data set, so there's some blue points here, there's some red points here. There's no way that I could come up with a linear classifier that's going to do well on this data set. However, what if I create a transformation that takes me up to 3 dimensions, where I keep the first 2 dimensions the same as the raw features, but in the 3rd dimension, I take the first squared plus the second squared. So this is just the squared radius. If this is the origin here, the new feature is essentially showing how far I am out from the center. And so here's what we get plotting that in 3 dimensions. We have the original features, these dimensions. So if I look down on this from the top, it would look exactly like this. But now we have a 3rd dimension, which is this feature. And you can see as the points get further out from the center, that dimension grows larger. And it turns out that all these red points here are further out, so they are all higher in that 3rd dimension. And now I can pass a plane right through here and perfectly separate into those 2 classes. So this is, again, similar to this, but just a little bit more concrete. Still, it's quite contrived. You might notice that in order to actually pull this off, I need to know a lot about this data in order to construct this transformation here. What if I had a different data set? Would this still work? Probably not. So the good news is that there's things we can do that end up working much more universally. So this is really just kind of a contrived toy example to illustrate the point. And the other thing is, typically the transformations we come up with will be into much higher dimensional spaces that we can't easily visualize. So again, this is just a low dimensional case that we can visualize. All right, any questions on this page? Okay. So this is how we might try to go about this. So this is the support vector classifier. This is the way we wrote it. Here's the hinge loss. Here's the scaling. Here's the regularization. and this is written in terms of zi. And as we know with any linear classifier, we write zi as b plus w transpose xi. Okay, but what we're doing now is instead of using the raw features xi, we're going to use the transform features, phi of x. So this is just some transformation. Typically, we start with some raw features and bring them into a higher dimensional space. So now, all we have to do to use the SVC with these new features is we just plug them in where we would normally see x, right? And as you can see, I now need to make w, my new set of weights, they need to adjust to match the dimensionality here. So like if I was doing my original features, I'd have 2-element w vector, but if I'm using these, I would need a 3-element w vector. Okay, so this is how we design the weights and the intercept. And then to actually classify a new test vector x, we would need to take that, transform that the same way, and then apply our weight and intercept to get the score, take the sign of the score, and finally we get our binary class. And so this is how you do it in principle. But the problem now is, what if the dimensionality of our transform features is very high? So the problem now is that we would need to make the dimensionality of w very high, and we would now have a very high dimensional optimization problem. When we run this in Python, it would take a lot longer to do because there's a lot more variables to adjust. So that's not great. Also, we might run into further issues if I'm not careful in how we design this transformation. Maybe we've introduced a lot of features that are very useless for classification, in which case we know if we have a lot of useless features and we still try to fit them, we have overfitting. So that's another issue that we could be faced with. So, and it might seem crazy to even ask about this, but what if I wanted to use an infinite dimensional transformation? So somehow I take my finite dimensional raw features and I transform them to some infinite dimensional space. Well, obviously, there's no way we can design an infinite dimensional W vector. We can't store that in a computer and optimize it and so on. So we're just done. There's absolutely no way to proceed. So it seems strange to even ask that question, but it turns out that the most popular SVMs are actually based on infinite dimensional transformations. So then the question is, well, how do you actually do that? You can't do it with the way that we are talking about here. That's impossible. So how do we do it? Okay. So the trick is to rewrite that SVC in a different way. It's called Lagrangian dual form. We're writing it in a different way that essentially doesn't involve the W parameters at all anymore. There's simply no more weights W that we have seen until now. So instead, we have these variables lambda. You can kind of think of them, they're related to Lagrange multipliers, but there's some parameters lambda, and you can see that there's this cost function that involves them, and you can see that there's some constraints, some inequality and equality constraints. Turns out that this is a convex problem, so it is possible to solve this. The other thing we might notice is that the number of lambdas is equal to the number of training examples. So whereas with W, in this case, the number of W parameters is equal to the number of transformed features, right? But here, the number of parameters I'm adjusting is not related to the number of features in X. It's related to the number of samples in my training data set. So that's kind of interesting. If you're just solving this problem, that could be good or bad, because actually, in most practical problems, the number of training samples is much larger than the number of raw features. So it might be that doing this in the typical case, where you don't have any transformation, would actually maybe be a slowdown, because you have more parameters to optimize. But it is just another method. If you solve this problem, you end up getting exactly the same answer. Unfortunately, the derivation is a little bit outside the scope of this course, but if you're interested, you can read about it in this book. It goes through the derivation. If you have taken a course on convex optimization, then this kind of stuff should be familiar to you, but we just don't have the background here, so I'm not going to get into all the details. But the main point here is that it completely bypasses the computation of W. So there's just simply no more W's. So if I can apply it in this context here, I can avoid those W problems that I was complaining about. Okay. All right, so any questions about this Lagrangian dual? Yes.
I have a question about reasoning.
Sure.
So, when we're using this method, does the model know when to stop, which dimension to stop, or do we have to just hardcode that you stop at this dimension? Like, when do we know? Or better question is, when do we know to stop?
Are you asking about how we define the transformation?
Yeah. So you're going from your example goes to the second 2-dimension to 3-dimension, and it worked well, but in other cases it might not, right?
Yeah.
So,
Yeah, so I think you're asking the question, how do I know how to design phi?
yes.
How do I know what transformation to use? Yeah, that's a great question. We at this moment, we don't really have a great way of doing that.
Okay.
So that is a big issue. On Friday, we will start talking about neural networks,
Okay.
and we will see that what they do is they actually learn this
Yeah.
from the data. So that will be the solution that we'll finally pose to that question.
But when we're using this, then we have to put in
Yeah.
each equation ourselves.
But here, we're sort of assuming that someone is just giving us this phi function that somehow works better, and then I can do this. It's an open question at the moment of how to actually come up with that. But that's a great observation. Yeah.
Okay.
Yeah. We haven't talked about how to come up with the phi function yet.
Oh.
But if we have it, then this is just a convex optimization problem.
Mhm.
We're just using our pre-processed features. That's it. We can just run this with sklearn or however. And in fact, this is just another way of doing the same optimization, but reformulating that same convex problem using somehow different parameters and solving that. And so here too, we're not even using any transform features here. This is just the original untransformed raw features being used here. But this is just a different approach that should give you exactly the same solution as this. But the important thing to note is that there are no more W's, so that seems to get around the issue with worrying about the number of W's. So that's what we're seeing here. Yeah.
Should there be other sub I on the second x in the I-hat portion? Like the summation there?
Oh yeah. So I didn't explain everything here. So the answer is no. So there's a sum over I, and that I is used here. And then there's a different thing called I hat. And I hat is any fixed support index. So if the first vector in your training set happened to be a support vector, you could use I hat equals 1. And for that fixed value, use that here and here, which is different than this I. Okay, so so basically just the way that this is written, you need to know, you need to find some support index in your training set and store whatever number you choose for that and just plug that index into here and here. And otherwise the other i's are sums. The other I you're summing over.
I guess the question I had was, if you look on the summation to the left of that, is there supposed to be a sub I on that?
On this one?
Yeah.
No.
Right next.
No. So this Okay, so this is your test vector. These are your test features so this is all training. So this is all training data. The goal in this step is to figure out what are these lambda parameters. You solve that problem and we give them the name lambda hat now that we know them. So you can see now these lambda hats are showing up down below. However, in this second stage, you're given a test vector x. You don't know the label. You're trying to figure out what is the label. This is your guess about the label. You come up with that guess by taking what you learned during training. Interestingly enough, you also need to involve your training data here, as well as your test x here. If you think closely about this, so it turns out, I didn't explain this, but it turns out that when you have, when you do this optimization and you look at the different lambda i's, if you have a support, if you have an index I in your training set that is not a support vector, that lambda I will go to 0. What that means is that all the terms in this sum that are not due to support vectors can be thrown out because they will give you zeros here. And so when you do this, you need to involve all your support vectors for a single classification. The reason I'm explaining this is because it tells you that the complexity of the SVC grows with the number of support vectors, even at test time. Even after you're done training and you need to test a single sample X, the complexity of doing that grows linearly with the number of support vectors that you found during training. So there's a computational cost. The more support vectors you use, the slower your inference, the inference stage, this is the training stage, or the test stage, the slower test becomes with the number of support vectors. That's sort of interesting. We never saw that before. Because when we're in this primal form, like in general, all the W coefficients are non-zero. Yes, there are certain elements of our training set that were not used to determine W and B, but nothing about this really changes in complexity. However, down here in this formulation, this becomes more complex computationally as you have more and more support vectors. Your code slows down. So you'll notice this in Unit 7 in the lab. As you increase the number of support vectors, your code will just slow down, and it kind of motivates you not to have more than you need because you just have to wait longer. It's kind of a pain. So that's an important thing. Another kind of high-level important observation about this is that the complexity of this ends up scaling as n squared. So if I double the size of my training set, I will quadruple the time it takes me to train my SVC. So complexity is big O n squared, grows with n squared. That is not something that we have in the primal formulation. In this case, it tends to grow linearly in n. So if I double my training set, it will take me twice as long. Over here, quadruples. So there's several issues that you have to be sort of aware of when you use this. Complexity grows quicker, and all right here, complexity proportional to the number of support vectors when you do testing. Okay. Yes? Number of support vectors, if you remember, is controlled by C. So when we had large C, few support vectors, small c, many support vectors. That's how we control number of support vectors. Now, as you take c to infinity, that does not necessarily mean your support vectors collapse to like 3 or some tiny number like this. If there happens to be like some black points over here and some white points over here, no matter how you pick that boundary, they are support vectors. So the more overlap you have in your data set, that determines the minimum number of support vectors that you could ever get. And then as you shrink C, from that minimum, you just get more and more and more. So that's what determines the number of support vectors. Okay, these are all good questions. Any other questions on anything? Okay, great. Okay, so now we have this method that we notice kind of bypasses all this computation of W, all these issues with the dimensionality of the number of features we have. So let's just plug in the transform features into these equations, and I've highlighted the changes in red. So all the changes are those. And you can see that, once again, as long as you can do this inner product here, you can tolerate as high a dimension of phi as you want. Like none of the other variables are growing in number. The number of lambdas is fixed at n, no matter how many of these transform features you have. That said, computing all those transform features still could be expensive depending on how you're computing them, and you still do have to do this inner product. So that scales linearly with the number of features. So with the number of transform features. So there's limits. And for example, if phi was infinite dimensional and you explicitly computed like this, it's not really clear, that you could do this, because it's like, well, I have now an infinite number of things that I need to add up in this inner product. Okay, but there's sort of a key point, is that when you look at this, you look at these equations, phi never appears in isolation. It only appears in this very particular form. Let's give that form a name, kappa. So whenever you see phi of one vector transpose phi of a different vector, let's just call that kappa, the first vector, comma, the second vector. That means that we can rewrite this as kappa xi comma x. This becomes kappa xi comma xi hat. And this one is kappa xi comma xj. So with this last version of the algorithm, in fact, there's no more phis. As long as you have some kappa that you believe in, that you can compute, you don't actually ever need to say what phi is. And that is basically the kernel trick. We only need to compute the kernel, never any explicit transformation. And it turns out that there are these great kernels that work super well, where the only way to write phi, if you tried, would be to have something with an infinite number of dimensions. So no one even tries to do that. You just work with kappa directly. At that point, the complexity of this algorithm, well, you need to evaluate your kappas. And of course, you still have n squared complexity during training. You still have complexity proportional to the number of support vectors during testing, but you can handle any transformation, even infinite dimensional, as long as you just work with its kernel, not the explicit phi. So this is the main idea now. This is the final piece of the puzzle. And so I guess the last thing is to talk about the different kappas that people tend to use. All right. Before we move to the next page. Are there any questions about this overall? What did we do? So we took this Lagrangian dual form, wrote it in terms of the explicitly transformed features, then sort of just almost as a notational change, wrote that in terms of these kappa functions, but finally realized that if I have a kappa, then I don't actually need any phi. And so we actually do have these great kappas that we don't even know what the phis are, but the kappa works great, so let's just use that. Okay. So here are the popular kernels. By far the most popular one is called the radial basis function. The key to interpreting all these kernels is that they all measure similarity between their two arguments. The more similar those two arguments are, the larger the value of the kernel. The specific definition of similarity is dependent on the kernel. So they all have different similarity definitions, so they will work better or worse depending on the data set. As we just saw, let's say that you have a trivial transformation. That's how we started with, for the SVC. So phi of x is just x. Well, in that case, the kernel is just the inner product between the two different x vectors. So as we know, the inner product measures something about the orientation. So if I have orthogonal x and x prime, I get 0 for the kernel. Okay. If I have non-orthogonal x and x prime, I get some positive contribution. I could get a negative contribution if the angle between them is actually obtuse. Right? And then the other thing we know is that it's not just about the angle. Actually, the length or the norm of x and the norm of x prime, that will also change this. But overall, it's measuring something about, you could say, about the angle between those two vectors. That's what is happening in the typical SVC from the kernel perspective. This most popular one, the RBF, looks like this. So here you have the Euclidean norm squared between x and x prime. Obviously, that gets smaller as x and x prime become more similar. In this case, it's similar in Euclidean location. And as that gets smaller, when you negate it and exponentiate it, this thing gets bigger. So the biggest this can become is when x and x prime are equal, in which case you get e to the 0 or 1. But any other x and x prime that are not equal will give you values for this kernel that are smaller than 1. And as x and x prime get really far away from each other, this thing goes to 0. So it's sort of a measure of proximity, but it's very nonlinear due to this exponentiation. So people say that this defines kind of a neighborhood among your samples. Two samples in your data set that are very close are treated as similar. Yeah, these things are similar, but then as you get beyond some threshold, because of this exponential, things just get very dissimilar. So it's sort of like you have this local neighborhood of similar things, and then beyond some threshold, it's just everything else is totally non-similar to those. So that's sort of the way that this works, and the performance ends up being really good for general data sets. So yes, for some it's especially good, for some not quite as good, but in general, you apply this to just about any data set, and it works better than this linear thing. There's other options. For example, the polynomial one. So instead of this exponential thing, you take that linear inner product, then you shift it, you scale it, you shift it, and then you take it to some polynomial power d. Usually d equals 2, but it could be larger. And this nonlinearity also kind of gives you this local neighborhood behavior. Or you could do a tan H. Tan H is similar in spirit to a sigmoid, but it's just shifted down. That's another option. And as we said, linear is just sort of like corresponds to doing our our SVC that we saw before, which is a little bit better than logistic regression maybe, but not that much better. But this is the one that tends to be used as a default. Okay, so questions about these different kernels? Okay. So in general, for a problem, you just have to try them. You kind of make a short list, go through, see how they work, pick the one that gives you the best cross-validation accuracy. It's probably going to be the RBF. Sometimes if you know something about the data, maybe you can construct some other custom kernel that might work a little better. Scikit-learn gives you the ability to do that quite easily. One last thing is to understand from the perspective of explicit transformations, like given this, how could we reverse engineer the phi? Well, that's pretty tough. We don't really know exactly what phi corresponds to this, but if we tried, we could try to get some intuition by expanding this exponential here into an infinite series. And we can do this as follows. So we have, exponential of the first thing, exponential of the second thing, the first norm, second norm. And then here's the infinite series, which has these inner products, but now raised to the jth power. And we actually have to look at the series for j going from 0 all the way up to infinity. So in some sense, it's like if you think about each one of these guys as a feature, and you really want to, do this, you would need to involve an infinite number of those features to make this RBF kernel. So working directly in that phi space is just impractical. However, by doing it this way, we avoid ever explicitly working in the phi space. We can evaluate this very efficiently, and it works great. So this is how we get around it. This is the kernel trick. Okay, so those are all the main ideas. Any questions? Is this sort of making sense? Yeah. Oh, yeah. So that's right. So the gamma is the width of the kernel. Basically, as gamma gets bigger, the neighborhood shrinks because there's sort of a cliff that things fall off of very, very quickly. So yes, that defines how big your local neighborhood is, how much, and that, yeah, you basically use cross-validation to try different values of that, and you see which one works best. Okay. Okay. So how you implement this in sklearn is quite straightforward. You have the svm.svc. You tell it which kernel. So for example, here we're going to use the RBF. That is also the default. You need to specify the kernel width. We're going to use this number 0.0073, which was found to work very well for MNIST based on this other website. Remember, you also need to specify C, which controls the number of support factors. And in fact, you want to jointly optimize C and gamma together. It's not enough to just guess at one or the other and tune the other. You really need to jointly optimize them because they affect each other strongly. So you need to do a two-dimensional grid search in cross-validation. It gets kind of expensive the denser your grid is, but it's critical if you want good performance. However, doing this and evaluating it on MNIST, we go from 90.7% accuracy to 97.1. Massive jump, right? Just going from the linear kernel to the RBF kernel. Now, instead of like 9% error, we're at 3% error. So that's great. We're only using a subset of our training data set. If we used all 50,000 training samples for MNIST, we would do even better. And this is how in that table that I showed you early on in the unit, you can get down to 1% error rate by tuning things a little bit more carefully, using more data, and so on. So this is not the state-of-the-art method, but it's pretty good. It gets quite close. Okay. So that's kind of the conclusion of the story, at least for classification. I guess not quite. So we didn't talk about what happens when you have more than 2 classes. So it turns out, usually we do one versus rest, right? And when we do one versus rest, the trouble is the number of training samples stays the same as our original data set. And we know that when you train the SVC, you get a complexity that grows quadratically in the number of training samples. So instead of using one versus rest, we also, way back, we talked about one versus one, which looks at unique class pairs. So if I had, let's say, 3 different classes, I would first look at this pair. I would design that classifier. Then I would look at this pair, design that classifier, and finally look at this pair and design that classifier. Notice that when I do this, the total number of training samples has actually dropped, right? Because I'm not using these at all. And so when I have less training samples, my SVC runs faster. And it turns out that there's really no loss to doing this. There's sort of a way to do the design this way, and even if you want, convert it back to the one versus rest. But this is how it's implemented in scikit-learn is a one versus one approach rather than one versus rest. So that's the first point. Any questions on that? Okay. The second thing is there's another method implemented in scikit-learn called the new SVC, and it gives you exactly the same answer as the regular SVC or SVM does. But instead of using C as a real number, from 0 up to infinity, it uses a parameter new that is bounded between 0 and 1, and it's more interpretable. This new is a lower bound on the fraction of support vectors. So that's nice because with C, if you set C as like 10 or 100, you have absolutely no idea how many support vectors you're going to get. If you use the new SVC and you use new as 0.5, then okay, I'm going to have at least half my data set will be support vectors. So it just kind of gives you a hint about what's going to happen. Every C has a corresponding new where you get exactly the same performance, so it's just a matter of like a different interface. Okay, so I think that's it for the support vector classification. All right. Any questions on that? Okay, so just very briefly, it turns out that there's a way to use all these ideas for regression as well. And I'll just describe it really quickly. So the idea here is to tolerate small errors that are in the interval between minus epsilon and epsilon for some chosen epsilon. So you as a user, you need to specify what epsilon is. Maybe you say epsilon's 0.1. And basically, you're saying, I don't really care if I'm point epsilon away from my targets or closer. That's all fine. But don't let me make bigger errors than that. Do everything you can not to make bigger errors. So you're just sort of changing the loss. So in terms of visualizing the loss, this is your loss function. So this is the difference, let's say, y minus y hat. So you're saying if y minus y hat is between plus and minus epsilon, the loss is 0, perfectly fine. But as it starts to increase beyond that, then the cost increases linearly. Try not to do that. So sometimes in some applications, this is a good idea. In other applications, this is a bad idea. But it is going to be quite robust because this grows at this linear rate. Another idea, so if epsilon goes to 0, you end up getting this picture, which would be instead of like squared error loss, this would be absolute error loss. That's something you can do. That's robust. This is a variant on that where you actually allow a little bit of error. So basically, to see how this works, you would start with the idea of the hard margin regressor. You would minimize the norm of W such that you keep all your errors in your training data between plus and minus epsilon. Okay, so just like with the hard margin classifier, the trouble is, well, what if that's impossible? What if there is no linear regressor that can do this? In that case, you can't apply this method. However, you can say, well, let's adapt this, so let's generalize this to a soft margin regressor that does exactly the same thing as this does, if possible, but if not, it gives a usable design. So what we do is we take this inequality and we write that as a loss, and then separately we take this inequality and we write that as a loss. So here's one of those inequalities. Here's the second, doing exactly the same things we did with the binary classification thing. And so now, this is our new thing. We can use this whether or not we can pull this off with our data set. We have to optimize C. That will determine the number of support vectors in our data set. We have to specify what epsilon is. So those are a couple things we have to tell it. And then the real big win is we can convert over to the Lagrangian dual formulation of this problem and then replace all the x transpose x primes with a kernel. So now we can enjoy this RBF kernel in regression. And when you do that, performance goes way beyond what you can do with your usual linear classifiers. Your like least squares linear classifier. Because now you're essentially doing this sophisticated infinite dimensional feature transformation according to the RBF, and it just works great. So you have all these implementations. This first one doesn't allow any of the, this first one basically uses the primal form. It doesn't allow the kernel. This one uses that dual form and allows a kernel. And then this one is the new formulation where C is instead specified by new. So that is, that's all for today. And that's all for this unit. So so on Friday, we'll get into what I think is the most fun part of the course. We start talking about neural networks. And I'll see you guys then.